Welcome, everyone. Thanks for coming today on day 3 of C++ on C. Hope everyone's having a good time so far. I'm Roth Michaels. I'm a principal software engineer at Native Instruments. We're a group of companies that came together a few years ago that work in the audio production space, making everything from software for mixing and mastering albums, post-production film and television, DJ software, keyboard, synthesizers, and in a lot of my talks, we use audio for examples. Today, we're just going to be nerding out about C++. So there's no audio in this talk, but if you want to talk to me about audio in the hallway track, please feel free. Before we get going, something I like to do before I begin all my talks is kind of give a call to action to anyone in the room or anyone watching online to consider giving a talk. Because myself or any of the other speakers up here are not some magical C++ deities, but are just people that have learned something, saw something interesting, and wanted something to share. And I'm sure lots of you out there might have something interesting to share as well. If you're haven't given a talk before, lightning talks are always a great way to get started. Also, if you're not aware of the Include C++ group, they have a Discord that also is a great place to go for feedback on abstracts and materials for your talks. So another great resource if you're thinking about getting into giving a conference talk, and I encourage everyone to try it out sometime. All right, so let's get going. Don't get overloaded by overload sets. As you'll see later, sets is the key word here. I was actually, when I spoke to a few of my colleagues and other developer friends about what my talk was going to be about, and I said overload sets, they were like, huh? What do you mean? I'm like, oh yeah, function overloading. And they're like, oh yeah, I know what you mean. But this concept of sets is something that people are not always thinking about, but is actually a key part of this. So what is an overload set? It's one of the kind of fantastic parts of C++ that we got as we moved away from C that gives us a lot of power. So I'll show you one kind of small example of this. In the C standard library, we have 3 functions for calculating the natural logarithm. We have the original one, a log, that takes a double and returns a double. But if you want to work in other precision, there are 2 other variations, one with an f at the end that takes a float argument, and another with an L at the end that takes a long double argument. So often in C, this is what you have to do if you want to have functions that take different argument types. Sometimes there's some magic you can do with macros to do other stuff, but yeah, don't worry about that. That's pretty yucky. We don't need to care because we have C++, and we have this great version of the natural logarithm. So as you see here, highlighted in orange, this is the overload set for the natural logarithm in C++. And you'll see there are 4 variations that take, again, float, double, and long double, and this extra one, integer, we'll mention in a second. But if you notice, we don't have to have any special prefixes. They're all just log. And then this extra one, log, at the bottom, can take an integer type of, any integer type, and technically the template could take any type, but let's not worry about that right now. It's supposed to be for integers. And it will return a double because if you take a logarithm of an integer, you don't really want an int out. That's not going to give you a useful answer. So that's why it's always giving you double. And the nice thing about this is you can just call standard log, and you don't need to really worry about what type you're passing in. You're going to get the right function every time. So let's look at another few other simple examples. Let's imagine we have some hypothetical 2-string class. This is kind of similar. We have a mix of some functions that take float, double, and long double and return a string. And then we also have a function template. Again, on our non-concepted integer class, look at my talk last year about concepts to maybe see how we could write that a little bit better. And that one returns a string. And so you can see all these functions are differentiated by their argument type. Now, imagine we want to do the opposite. We want from string that they all take string arguments, but return float, double, or long double. Yeah, this is not allowed. And you'll get a diagnostic like this saying that functions that differ only in the return type cannot be overloaded. The under the hood reason is, I guess, design reasons. Most of the name mangle in C++, like that information is discarded from the in the actual linked binary. Most of the time, that's not true in MSVC, but in general, that return type isn't part of the function signature. It's just the name and its arguments. But the one interesting exception to this is the template. We're not going to get into a lot of this talk, but I do want to call this out. This template actually allows you to specify the return type because the template is actually kind of a special name that's applied. So you might see that. We're not really going to get into that too much in this talk. If there's some questions about that later, please feel free to ask. And speaking of questions, I forgot to mention at the beginning, if you do have questions along the way, please raise your hand and I'll be happy to answer questions as we go, depending how we're doing on time. I might ask you to wait till the end or until another slide comes, but happy to take them as we go because we're going to be covering a lot of material and some of the stuff gets a little weird because it's, C++. So one place I'm sure all of you have encountered function overloading is with constructors and different types of constructor arguments. And vector is a great example of this. So we have 3 different vectors being constructed. First, we have an empty vector. Then second, I create a vector of 5 elements. And then we create a vector that has 5 specific specified elements. And the second one, they're all initialized to 0. One thing to note is the third version is taking the initializer list with braces, but we have to use the parentheses for the second one to make sure we get the right overload. Later, when we talk about how overload resolution works, we'll see actually why that is, but just keep this slide in mind for later. Also, interesting to note that we also get the right thing for the default constructor if we put the braces there. So there's 2 kind of special rules of function overloading for braces. Again, this will come back later in the talk. So what do these actual constructors that are overloaded look like? This is a set of constructors for vector. There's, I think, a little more in C++ 26, but don't worry about that. This is what we need for the talk. So we see these 3 constructors. The first one is the default constructor. The second one is something we'll call the fill constructor. And the third is an initializer list constructor. And we have these 3 highlighted in orange here. You also notice there's some default arguments, allocators. We don't really need to worry about that stuff. But keep in mind, later when this comes back, that we have one constructor that takes no arguments, one that takes a size and some other stuff, but we're focused on size, and the other that takes a special initializer list class. Another kind of function overloading you might encounter a lot are the special member functions for copy construction of either L values or R values. We're not going to talk about that so much, but I just kind of wanted to highlight that here as well. So what is an overload set? And what do I mean when I say set? So imagine this situation. The overload set is essentially a name representing a set of functions that are found through name lookup. So imagine this scenario. We have an outer namespace A. We declare some function foo that takes an int argument. Within that namespace, we have a nested namespace B that has 2 different overloads for foo. One that takes a character argument and one that takes a long integer argument. And then we have this function bar that takes an int as an argument and then passes that int on to foo. So in this case, we kind of have 3 options of what's going to be called. Is it option 1, 2, or 3? No, it's actually neither of them. The call here to foo is ambiguous. And we'll see, we'll take a look at why that is in a moment. The reason is because in the context of foo, or I'm sorry, bar, there are 2 copies of foo that are in the same scope. So when we're looking for names, those 2 names are found, and that is our overload set. But integer can convert to both character and to long, and the compiler doesn't know which one you mean. So that's why it's telling you that it's ambiguous. We can fix this though. If we know, like, oh yes, we don't want to lose precision, so we're going to cast this. Sorry for the C-style cast and not static cast. This is just to make room on slides. Please use static cast instead. But if we cast this to a long, now option 3 will be chosen. Or if we want to lose some data potentially, we could cast it to a character, and option 2 will be chosen. So again, looking back at this example, what if instead of bar being a namespace B, it's in a different nested namespace C? Which one is going to be chosen? Any guesses, show of hands, for option 1? Option 2? Option 3? Okay, you guys are already, I think, getting the name of the game here. Yes, is indeed option 1, because in this case, we find no foo in the scope of namespace C. So we're going to move up to the next namespace and look for foo there, and we find option 1, the foo int, and that will be what it's called. We could also select the overload set in the namespace B if we're explicit and we qualify that call not by just saying foo, but A : B : foo. That means we only want the foo that's in namespace AB. And then that is the overload set again of the two foos taking the character and the long. So now I'm going to kind of really illustrate what I'm talking about overload sets. If we use the type ID operator and call that on A : foo, that will give us a type info object. If you're not familiar with type ID, it's not really relevant here, but essentially it takes a type and then gives you a runtime value that can give you information about that type, such as its name, etc. But what I'm trying to illustrate here is that works fine. But if I call type ID on A : B : foo, I will get this diagnostic. Reference to overloaded function could not be resolved. Did you mean to call it? Did I mean to call it? No. Why is the compiler asking me this? Well, it can't know what overload I mean if I'm not actually passing any arguments, and so I actually would need to call it. The same issue will show up with decal type. If you're not familiar with decal type, doesn't really matter for this talk, but essentially it will tell you the type of some declaration. And again, it's going to tell you, yeah, I don't know which function, like I don't know what type this is because you're talking about multiple functions and they have different types. If you actually want to get at one of those functions, you can do this. Again, sorry for the C-style cast, but if we cast this to a function pointer, then we can actually specify, no, we mean the one that has a car. So hopefully you're starting to see what I mean by overload sets, is that you either have functions, and those are single entities, and you can take their address, use them as pointers, etc. But an overload set is this concept of multiple things, and you actually must call one for one to be chosen, or cast it to one of the specific types. But normally, we're not doing that, and it's calling the functions that actually decide what's going to be in the overload set. So before we talk about actually how the overload resolution works and how we find out what function will be called, we need to first find out how do we even find what overload set we're going to use. There's a lot of details here, but I'm going to try to kind of keep this as simple as possible. But essentially, you're searching scopes. So you're going to search the current scope for a name. And I'm talking about namespaces here. Like if you have functions inside of functions, also the scopes searching there also kind of happens. But let's just talk about namespaces today. So we're going to search the scope for a name. If we don't find it, we're going to continue searching parent scopes for a name. And when a name is found, all the overloads that exist in that one scope, not some other scopes, except for ADL, which we'll talk about in a minute, but that's the overload set you found. If you're in a class scope, calling a qualified static member function like C : foo, or a member function, C .foo, then we're actually going to be searching only the classes and base classes looking for that overload set. And interesting thing to think about here, classes are essentially also a namespace. They do some other features, but really functionally they are namespaces. So what if we're not qualifying it with a name and we don't know what namespace to look in? Like if, earlier we saw in this example, I'm qualifying it with the A : foo, but if there's no qualification, there's some extra stuff happens that comes into play that maybe is sometimes surprising until you first find out about that. So again, we're going to search the current scope for names. We're going to search parent, and if we don't find one, we're going to look up all the parent scopes until we find some set of names. Let's find that name and then that set of functions. If we find a name that matches that, but it's not a function, like it's a name of a variable, that doesn't count. We're moving on. And then actually that should say if found or not. There's also argument-dependent lookup that happens. And the way this works is for your function call, if there's any argument is a class member, that class's namespace, the base class's namespace, and the parents of all those namespaces will be also searched for potential names that match. If it's a namespace member, we'll search parent namespaces. And it's not just the arguments. Even the template parameters, their namespaces will also be searched. So It's kind of spooky action at a distance where you search your scopes, and then there could be some other namespace over here that we also discover some potential matches and coalesce those into one overload set. So let's take a look at this. Again, looking at our previous example of our namespace A with the one foo overload, namespace B that has two foo overloads. But now we have this other namespace. And in that namespace, we have a struct S and a foo that takes an S as an argument. And this time in bar, we're calling foo and passing an S object. And sorry, I'm realizing that it should actually say other namespace : S. But what happens here is that assuming that other namespace it was actually there, we know that, oh, let's look at our current namespace, B. Okay, we found two foos. That's in our overload set. Now we're going to go to the namespace that S comes from. And in that other namespace, we find, oh, there's another foo that takes an S. And so in that case, we have three functions in our overload set, two that are in our current scope, and one that's from somewhere else, but it has a matching name. Yes, please. Oh, that's going to come back at the end. So the question was why we're skipping variables. Like if we had a lambda variable that could also take arguments. Oh, spoilers for the end. That doesn't participate in overload resolution. And it's a fun trick. If you don't want overloading, make a variable function. But so we'll come back to that tip at the end. But that is why they don't participate. A function object is not going to participate in that overload resolution set. So why do we have this ADL? Like when I first heard about this, I was like, oh man, C++, crazy language. But it's actually what gives C++ some of its most powerful features that is like, I don't get to use in other languages. A big one in C++ is operator overloading. Early in my life, I took a Java 2 class, which was an anti-C++ propaganda class, and they told me how horrible it was that you could overload operators. But it's actually something we do all the time because we don't want to just deal with our basic built-in types. We want to be able to add geometry types like points or vectors or tensors. So there's all sorts of things that might make sense to add that aren't defined in the language itself. So it's kind of an incomplete example. We have some type foo, does something, and we define an overloaded operator plus that takes foo as arguments, and then we can, have our n : foo created with 40 and add it to another foo, and that plus resolves the right operator, and we don't need to actually know what namespace that came from. Imagine if any time you added anything that wasn't a primitive object, you had to know what namespace the plus existed in, and then if you put that in there, it no longer looks like plus, and the kind of point of overloading goes away. So that's one part of the beauty. The other reason we want ADL is generic programming, which is another big feature of C++. We're not going to really talk about that too much in this talk. I've given most of my other talks are talking about templates and metaprogramming and other stuff. Please check those out if you're interested. But this is one kind of small example. Imagine we have some template called getFirst that takes some type and it calls a get template on it, templated on 0, and passes that type in. So we can call this with the standard library pair, and then that get is going to go, okay, there's no get in scope, but I have a standard pair as an argument, so let's look in the std namespace. Oh, there's an std : get. That's what we'll resolve for that get. We can also use it with boost pair. And when we do that case, we go, okay, we don't have a get in scope, but we have a boost namespace in the argument, so let's go hunting in that namespace, and then we'll find the right boost : get, and that's what will be used in the second example. Now, keep in mind, of course, this is C++, there's header includes. If you haven't included it, it's not going to get found. There's no magic like this. No comment on modules. I've not been able to try that because of supporting Apple platforms and Xcode, and I don't get to try that out. But yeah, so generic programming is the other motivation for this. Okay, now that we know actually how we find the overload set, how does the overload resolution actually work? How do we pick which function gets called? We've got to find the best one, right? You wouldn't want to call the worst function. So how do we decide what is best? Well, there's an exact match. The argument you pass in exactly matches the type of the parameter for that function. If that is not an option, the next thing we try are promotions. So those are conversions from built-in types. They're not going to lose precision, like a bool or a short being promoted to an int. Next are other conversions, like all the implicit conversions that we have in C++. Please turn warnings as errors on W all, or at least the W conversion ones, so you don't get surprising bugs with this. But we try any mashing of numbers into other shapes to get that to work. And that's why we have these two levels. We want to try promotions first, because we know we're not going to lose any information. But if that doesn't work, yeah, okay, we might lose some information. Maybe not, we'll see. And then if that's not an option, we do what a user-defined conversion is. And that's essentially, and when I say user-defined, it's not necessarily you. The standard library writers also can write user-defined conversions. That's essentially any time a type can convert to some other type. For example, if you use string view, you can convert a string to a string view, counts as a user-defined conversion. And then also we have this ellipsis kind of from C that says, okay, yeah, we take some arguments, and that's kind of the last default. Again, hopefully you never need to write the ellipsis. Old metaprogramming stuff kind of needed it, but that's one example. So let's check this out in practice. Imagine we have this set of, is it 6 functions? Yeah, 6 functions in this overload set. Taking int, short, double, long, string view, and ... So if we have an int 42 and we call this function, it's going to call the function that takes an int argument, because we're doing exact matches. We're going to go through all the examples in priority order. So this is the best of the best. Or if we have a short that's 42, that's going to call the select function short, because again, we got a best match. Now we'll look at promotions. That's our next best option. So if we have a character A assigned to C, and we call this function with C, well, there's no character in our overload set, so all right, we don't have an exact match, but character is allowed to promote to int, so we'll call select function int. Same thing with bool. We have a bool b that equals true. There's no bool in our overload set, but we can convert a bool to an int, and again, we'll call the select function int. All right. Now the one that hopefully you have warnings on for, but actually in this example, we're not going to lose precision, hopefully, because we're going from float to doubles. But if we have a function that just passes in 42.0, that's going to call the double version of the function. And if we have a float f, 3.14 f, and pass that in, well, there's no float, so we can pass that to the double version. And now we're getting the user-defined conversion. So if I call this function with a literal string, which is a constant pointer to constant characters, well, that's nowhere in our overload set. But there's a constructor for string view that takes that as an argument. So that means we can convert that to a string view. And you're allowed one user-defined conversion. You can't like go thing to thing to thing to thing. Yes, please. Oh, the question was that this works because the constructor of string view is an implicit, as in no keyword. As usual with C++, the more dangerous thing is the default. But if you don't put the explicit keyword, these conversions happen automatically. If you have the explicit, you must do a cast. So the opposite, for example, the standard string has a string view constructor, but that is, or actually I'm not sure if it's that or the string view has an operator, but the conversion the other way from like a string view to a string is explicit. And when we come back later, we'll see there should be an example later slides of that explicit, but thanks for that clarification. This only works if you don't have the explicit keyword on the constructor or a conversion operator. And in our last kind of ugly example, we have some struct, the mystery type. We create one of those X, we pass it in. Mystery type is empty body. There's no, standard library string view doesn't know about it. It can't convert to any of these things. So we're going to call select func ellipsis. So again, going over what counts as the best match. We can look for exact matches, promotions, standard conversions, user-defined conversions, and then the ellipsis. But if you remember back to the beginning, I mentioned this braced initialization, And we've got some special priorities that go on there. So for any function in your overload set, if it takes an initializer list and you actually call that function with passing braced initializer lists in the arguments, as long as the types in that can convert, that initializer list is going to take priority over any other matches. And that's kind of necessary to have the braces have initializer list constructors work. And then if you're talking about constructor overloading, constructing with braces even is a higher priority, where the default constructor is going to get picked if it exists over passing nothing to an initializer list. So looking back to our original example, we see that the bottom, where we're specifying specific elements, that's going to call the initializer list constructor, initializer list int constructor of our vector. But if we pass it no members in the braces, that's going to even take higher priority and say, oh no, that's not an initializer list, that's a default constructor. And that's why the trick always, I'm preferring to always use braces, and the only time I don't is when I need to call some other one in this special case where we're passing vectors of ints, and if there's only one int, I can't use the braces, because that would, if I did 5 there, it'd make an element of one vector with 5. So I have to use parentheses, so we're not prioritizing initializer list and defaulting back to the normal rules. Yes, please. Oh, yeah, so the question was about like the most, this is sometimes called the most vexing parse in C++. He's asking about how we know that this is actually declaring a variable v2 where we're constructing it with 5 versus how do we know it's that versus this isn't some function v2 that is taking the vector. In this case, I wasn't prepared exactly for this question, but I believe the answer is in this case because we're actually passing in that 5 there and there's no types in the list. If we call that with no arguments, I think it might be kind of context dependent when that works. But let's circle back to that question at the end, because that is a great gotcha, and I've got some other gotchas to show you, but I wasn't actually prepared for that one exactly. But let's circle back and we can maybe dig into that one at the end. So what if templates are involved with overload resolution? So let's look at this case where we have 3 overloads, a template that can take any t and claims it's going to perform a square root, another template that takes a t in the template parameter, but the argument of the function is a standard complex of that t, and then we have a square root of a float. And so imagine we have this function do square roots that takes some standard complex float z and then calls square root 3 times. First with an integer, then with a float, and then with our standard complex. So the way this is going to work is first we're going to take a look at the templates and see what templates potentially match. In this case, the top template, we can definitely pass 42 to that. There's no restrictions. But 42 is not a standard complex of any type. So that template is not going to work for this case. So in that case, we have 2 options. The square root template on the top and the square root float are in our overload set. And float is not an exact match for 42 because that's an integer. But class T, you can insert integer into there and that will match anything. And so it's going to pick the top one, the template. In the second example, we're passing 3.14 as a float. In that case, again, we look at the templates available. We're allowed to use the top template with floats, no problem. We can't pass a float to the second template because it wants a standard complex. And we can pass a float to the square root float. So we have 2 options in our overload set, the template at the top and the function at the bottom. In this case, if you have 2 things that can win, and one is a template and one is not, the real function wins. And we'll get to it later one of the tips, but that's a reason to sometimes prefer plain functions if you don't really need to be using templates. And the last example, we can see that, again, if we go from the bottom up, okay, we can't pass a standard complex float to the bottom one because that only wants floats. We can pass it to the middle one because that wants a standard complex of something. A float is fine. And theoretically, we could also pass it to the top one because that's going to take anything. So we have two options there. And before we even get to overload resolution, we got to pick what's called the most specialized template. There's a lot of rules about this. The way I like to think about it, though, is imagine which template could take more other types. There's only a small set of types, basically std complex something, that will work in the second template. But really anything can work in the first template, which that makes the second one more specific or more specialized. And so that's what's going to be chosen in that example. So again, to kind of go over what the rules for this are, first we're going to find all possible template specializations. We're going to look at only the ones that are considered most specialized. So in the last example, that was the standard complex one. Then we're going to perform overload resolution on our most specialized templates, plus all of the normal functions, and try to find our best match. If two matches are equally ranked, the function wins over the specialization. And if there's no equal ranking, or there's not a function, if there's equal rankings and one's not a function specialization, like things are really equal, we're back to that diagnostic from the beginning saying it's ambiguous, we don't know what to do. Anyone surprised by this? Templates can be surprising. A few years ago, I was preparing a talk, and I asked, I think this was ChatGPT 3.5, for why one of my concepts examples wasn't working. And it told me C++ templates are really complex. Then it quoted part of the standard to me that I don't, well, it's kind of related, but didn't help. But that was a few years ago. These things are better. But moving on. So in this example, we're going to kind of show you a surprise gotcha that you can get with templates. And this is maybe a poorly designed class that causes this problem. But you'll notice it has a few features. I'm going to kind of cut out some of the stuff in a moment because we don't really care about the constructors. But basically, this myInt class or maybe int, sorry, is a, you can think of it like a standard optional int, but a little bit different. So it has two members. Basically, it has a potential value and a bool telling you whether it's valid or not. But if you notice now, when I kind of slim this down so you can see, there's a few conversion operators. So we can convert this to bool. When we do that, that's how we check, is it valid or not? And the way it's valid is if we actually pass in a constructor argument for the int. If we default construct it, we consider that invalid. So if you pass in 0, valid. Default construct, the value is 0, but it's invalid. And then we also have a conversion operator to int, the internal type, so we can just like, and there's no explicit, so even if invalid, we're going to convert this to int if we pass it to a function that takes int. And then we also have one that, this is actually kind of based on something that was a template in real code that I saw that was a less great standard optional because it allowed you to work with default constructed types and get values out even if they were not valid. But okay, we're in the future. C++ 17, we have standard optional, so we want to be able to use that in new code. So we added a conversion operator thinking that will save us so that we can just, again, implicit, and we can just, anytime we want to pass a function that takes a standard optional of an int, we can think, oh, we'll pass one of these things, and it will work great. So if you look at the bottom, I have a little bit of code where I first initialize it, maybe int, then I assert, then when I convert to bool, that it's false, and you'll see that because I've default constructed it, so mvalid is false, so the bool conversion will return that, and it'll be false, and so the bang operator will make the assert true. And I would hope that if I then created a standard optional with this, the desired behavior would be that would also be invalid. So that's why I have that assert there. But it's orange because, no, it's not true. Actually, when we do this, the standard optional says it has a valid value, and that value is 0. Why did this happen? Well, let's take a look at just some of the constructors that are overloaded for optional. We have one that takes an optional of some other type that can be converted to, and I'd be like, oh, actually, like we would hope that this one is going to get called because we're going to go from our int, it has a conversion operator to optional, which is what we want. It'll still be invalid and all is good. But, so yeah, we were hoping that this one's going to get, this conversion operator is going to get used and call this function. But actually, we get this one. And this comes back down to best matches. Because the first one requires us to convert our maybe int into an optional. So that is like number 4, user-defined conversions. The second one is taking anything. Anything is an exact match for anything. So in that case, we just pass in this case, u is maybe int, and we pass that in. And internally in the implementation of this, that will then construct an integer from our maybe int and actually call the int conversion operator instead. And yeah, this is a real issue we ran into trying to merge a silly optional type and some legacy code into something real. Also, another surprise, I've actually ran into this one implementing some custom random number generators, and where you could take a seed sequence or an individual seed, and the seed sequence constructor is a template. So if I have int x 42, I'm just going to seed with a single number. I would hope that would call the uint 42, just the one that takes an integer. I'm not passing a seed sequence. Why would I want this second one for seed sequences? But again, I'm going to get option 2 because int is not an exact match for uint 42, but it is an exact match for t because t can be anything, and anything's an exact match for anything. So yeah, be careful about overload sets with templates. They can be surprising sometimes. So what about member functions? And remember, as I said before, classes are namespaces. So in this case, this is pretty basic. We have struct b1 as overloads foo, int, and double. We create, oh, sorry, it's a typo. I should be b1 there. You'll see later slides, it says d. But if we create one of these objects and we call it with 42, yes, it's going to take option 1, the int constructor. Now here's where things get tricky. There's concept of hiding you might have heard of, which is if we have a struct b1 with a foo with an int argument, and then we derive from that struct d derives from b1 and has a foo with a double argument, and then we create a d and call foo with 42. Well, if we think all the foos are available, we think, yeah, we're going to get the int option, option 1. But we actually get option 2. Because remember, before I explained overload resolution, we first had to find the overloads in our scope. So, oh, D has a foo, so that's the one we're going to use. And there's only one overload in that overload set. We don't need to go up to any parent scopes because we found something. Here's another kind of actually, this is one of the examples that inspired me to do this talk when a colleague ran into this. We have a lot of mix-in stuffs in our UI library that brings in a lot of special functions that take empty structs to do magic. If you look at my CPPCon talk about GUI libraries, you'll see some info about that. But in this case, we have some structs, S1 and S2. We have 2 structs, B1 and B2. They each have a foo, taking S1 and S2 respectively. And then D derives from B1 and B2. And we would think like, oh yeah, there's no ambiguity here. Like S1 doesn't match S2. It does match S1. So of course we're going to get option 1, right? No, we have the diagnostic member foo found in multiple base classes of different types. Again, this is because name lookup happens first and then overload resolution. And so we're going to, okay, we have no names in D. Oh, we have names in B1 and B2. Like which one do you mean? So if you're using multiple inheritance, again, one of the things that I was told as a teenager was the evils of C++, but it is actually can be quite useful. If you're doing this, you can fix this by using a using um, declaration where we're going to say using B1 foo and using B2 foo inside of D. And what that's going to do is bring the names in from B1 and bring the name in from B2. And now these names exist in D. And there's now both functions are part of that overload set. And now when we call S1, it goes, oh yeah, okay, I found a name, an overload set in D. It has two options, S1 and S2. S1's a match. We'll call option 1. Yes, please. The question was that if we qualified that name with a : B1 or B2 to pick the option we want, would it select the right one? I believe it does. The use case that like this example came from, like no user code actually calls that. It's a lot of machinery, so that's why we had to do that. Because we actually want the full overload set to pick what we're going from. But yes, that should work to explicitly qualify that. So what about member function overload sets? And that you can qualify them. In addition to the normal, we just saw kind of normal overload sets, but now there's also qualification. So sure, this is pretty familiar to folks seeing const on some member functions. In general, it's a different topic for a different talk, but if a function can be const, please put the const keyword on it. Your colleagues will be very happy when they want to use that as a constant somewhere else in their code. They can still actually call that method. So we have some data holder that has some big data of bytes in a vector. And we decided to overload this with a const qualifier because if the member is const, we don't want to copy this data out. We can just read it, the read-only const copy, and return a const ref from the const object. The way this works is if the object itself, i.e. the implicit this pointer, is const, like if I declared a const data holder, then the const qualified method will be called. If I have a non-const object, the access data will, without the const qualifier on top, will be called, and then we're going to actually copy the data out. So that's a common use case for const qualification. Another variation of this is we actually wanted the non-const version to be able to modify the internal data. We can return a reference instead of a copy. Just depends really what you're designing for in your use case. We can also qualify things with reference qualifiers. You don't see this as often. It's usually kind of you're making certain vocabulary types where this might be useful. But imagine we wanted to be able to move the data out. We don't want to copy it out, but if we had a temporary data holder, we would want to actually be able to move that data out. So we can actually make 3 variations. We have the non-const reference. So in this slide, if you look at the first 2, the single ref on the first 2 overloads, that's implicit in this case. If you're not making it, there's an implicit reference qualifier on that. But then we have this third one that takes the ref overload for an R value reference. So if we have an R value reference in a temporary, then we're going to cast our data with student move. So it's now an R value reference. And then if you construct something else with that, you'll use a move constructor. I think I've written I can count them on my hand. I don't know if it's 2 or 3 classes that have done this. This doesn't come up very often, but I wanted to show you that it exists. And you often hear about this stuff as these qualifiers as const volatile qualifiers. So you can do this with volatile at the end as well. Yeah, forget volatile exists. Just please don't worry about that. I'm not showing any examples. So I'd like to look at a few tips. What if you don't want your overload set to be mysterious? You don't want to be confused by ADL. You don't want someone else to open up a namespace and add more overloads. You want to know you're designing a component for reuse, and you know you want your client code to be able to only call these functions. One way of doing this is, so in this example, we have structs S1 and S2, and instead of just having free functions, foo, that take an S1 or an S2 argument, we instead create them. Again, there's a theme here of going back to my old young person learning Java days, we put them inside of a struct and have static methods instead. I'm not normally going for this style. One of the C++ core guidelines says if something doesn't need access to private data, you should make it a pure free function. And in this case, there is no data. This is just a struct that just contains some functions. But you get some interesting features out of this. No one else can reopen my struct. Once I do that closing brace, that's it. That is all that's ever going to be in that struct. No one else can add some other header and add a S3 or a float to that overload set. I can't use using to bring this struct, these functions out of the struct into some other namespace, because you can't use using on members of a struct. And also, this defeats ADL. If you're, because you can't, you have to name and qualify this. Like ADL is not going to happen. So this is something I saw in John Lakos's large-scale C++ architecture and design book, and it's kind of a way of making a component that is isolated. You know, like this is kind of the whole world of this component. So just something, I don't use this often, but it's something to think about. Yes, please. Yes, so that's very interesting question. The question was the difference between using a struct and a namespace. So structs and classes kind of count as namespaces in the standard when there's a lot of things that say like you're searching namespaces for things. They kind of follow those rules, but they have extra restrictions. And those extra restrictions are a few things, and that's what kind of gives this trick its power. One is you can only open and close those braces once. So if I had namespace my component, I could have these two functions in one file, and then another header file have namespace my component and add more overloads. So this is kind of forcing that the whole API is in one place and no one else can add stuff to this scope, is one thing. The second thing is you can't, in some other scope, like I can't open Roth's crazy namespace, Roth's doing something crazy, using my component : foo, it's going to tell you, oh, you can't using that into this. So you always will have to qualify this with the my component : in this case. And the third one, that spooky argument dependent lookup. Imagine struct S1, S2 were in some other namespaces. We would never go looking in those namespaces. This is the full overload set. So it's kind of a way of constraining everything. So ADL doesn't happen. No one can add stuff to your struct. And there's no way to pull these functions out into some other overload set, except for the inheritance example I showed you earlier, but you can't like pull them out into global scope. Does this make sense? Thank you. Yes. So yeah, the issue that was just pointed out is that if you get the signature wrong, like if in my the CBP file, I write trying to get the definition for this foo, and instead of my component foo S1, imagine there's some S3, I use S3 instead. In the case of the struct, when I spell out my component : foo S3, it'll tell me, oh, that declaration doesn't exist. There is no S3 overload in this struct. But if you're just doing free functions in a namespace, it just becomes, oh, I can just declare any new functions in my CPP file. So that's another bit of safety, is it kind of makes sure you're not going to accidentally define, when you're thinking you're defining one of these declarations, actually ending up writing a new declaration for a new function. Thank you. That's another piece of power that comes from this. Was that one also clear? Thank you. Okay, another tip. When there's a choice, they actually don't write function overloads if you don't have to, but use default arguments. So this is actually the example from the C++ core guidelines for this guideline. When we use, imagine we have the bad example in orange in the bottom. We have two print functions. One that just prints just a string as is, and then one that prints a string with some formatter to do some special formatting thing. And you can imagine the way this is implemented is the first version might even call the second version with some default constructed formatter. And if you have the option, when you're having different numbers of arguments, you can, it's often a lot nicer to, instead of writing an overload set, to actually just write one function and default the other argument. So that's your next tip. All right. It's been spoiled, but we'll show it anyway. Here's what I meant about the variables. So if you want something not overloadable, you can make a lambda and assign it to a global variable, and it will behave just like a function, but there's no overload sets. That name, when it finds a name, it's like, it's not like, oh, I found a function, like here's my overload set, let me do overload resolution. It's like, nope, I found a function object, it has a call operator, and I'm gonna call on that. So I haven't actually had a personal use case to do this. I know a few colleagues I've seen write this. I don't know if it was just a personal style of liking writing things this way. I'm not exactly sure, but this is a trick that if I wanted to say like, okay, I want my my printer function to only take a string view. I don't want anyone to like say like, oh, it can take string as a value also. I want it to always be string view. This is just the one and only. Yes, please. Yeah. So the question was, is this about lambdas or is this about any variable for an object that has a call operator? And yes, that is true. That this is because essentially what a lambda is essentially syntactic sugar for making a function object that has, in this case, a single call operator. But if you write a class that has multiple call operators that are all overloads, then those will overload with each other, but only within that class. You're not going to get some other object. So again, remember there's two phases. Name lookup will find my printer, and then we'll be able to call that. In this case, there's only one overload, but if it was an overloaded function object, then overload resolution would happen on those members. Yes, please.
Microphone. There is another thing also. If in this case you have a fixed argument that is the string view, but if this had an auto so that it's essentially a template, then my printer is still one object that refers to the whole overload set of all the templates. Whereas if you had a freestanding function template, there is no way to refer to the whole overload set of all template instantiations.
Yes. Yes. Thank you. And it's actually I like essentially, and I have a slide on this later. But essentially, template functions are essentially like recipes for overload sets. And then with auto I love auto in lambdas for this exact reason, that you can kind of create these overload sets this way. Yes, please.
Yeah, I'm still not getting how my printer would interact with the namespaces in this case. Let's say you have a namespace A that has a function my printer, a namespace B that's nested in A which has this lambda, and then you're unqualified calling my printer from a nested namespace C inside of that namespace B. How?
Oh yeah, so it's going to do the same thing. So we're going to do, because name lookup is a separate thing from function overload resolution, because names can be anything in C++. They can be types, they can be variables, they can be templates, they can be functions. So in your most nested namespace C that has no my printer, it's going to find nothing. So it's okay, let me look at the parent namespace. It will find this const expr lambda my printer and say, okay, job done, name found. And now it can call that. And it's not going to keep looking for more function overloads in the other namespaces. Also, actually, I'm not, that's an interesting question. Maybe if anyone's interested in playing with the hallway, I'm not sure if this also defeats ADL or not. I think it does, but I'm not, anyone wants to experiment with me and Godbolt afterwards, we'll play around.
I'm reasonably sure it does.
Yeah, it probably does, yeah. I think so. And accidentally copied that slide, sorry. But yeah, ADL is probably, so yes, so you won't find, for the name lookup, you won't find that, but unqualified, you probably will find other things via ADL. Yeah, yes, I'm quite sure you're right, that is the case. But again, if anyone wants to play with Godbolt after, we can check it out for sure. Or, sorry, Mr. Godbolt, Compiler Explorer. So another tip is, again, from the core guidelines, only overload for operations that are roughly equivalent. So imagine we have two functions. One, open gate, for opening the gate to let us out of the conference before they lock us in. And then fopen for opening a handle to a file. Well, these are both opens, right? So like, hey, no problem, just we can call them both open. But this is really not what you want to do, because users will expect the same behavior regardless of the type. Especially in most cases, and really that's how you should design your overload sets, is that this is a name that does a thing. And then yes, we're giving you a lot of overloads to let you easily call this with various types, but we're expecting it to do, one thing. So in general, all of your overloads should have one user-facing behavior. Of course, in one of our graphics libraries, we have an image class, and you can create it with a special struct with a string in it that will say, okay, looking for a resource embedded in the binary. Or you can construct it with an array of bytes or a few different other ways. And under the hood, how it actually creates the PNG from this is different. But to the user, the behavior is the same, where I get a legitimate image object out of this, regardless of what's happening. There's one kind of subtlety here where you might want to have it be this, like, it's the same purpose and use case, but there are maybe sometimes where you do want a user control over behavior. And that, like, you could do different names, but there's this other functionality called tag dispatching. And this is used in the standard library. So normally when we use the find algorithm for the standard library, we pass it an iterator to the beginning of a range, iterator to the end, and the value we're looking for. But in more recent C++, there's this overload that also takes an execution policy as the first argument. And this will allow you to do stuff like saying, oh, you can perform the find in parallel, and there's some other options. And what those policies are essentially structs. In the standard, it says the bodies are undefined. Normally, when you're writing code that does tag dispatch, you just make empty structs and just, they're always a best match. And that allows you to pick the overload that's going to do your special behavior. And the reason why you might want to do this instead of actually giving it a different name, like find parallel or find sequential, is for kind of two reasons. One, people already use this API, and you add this new feature or parallel, so they're used to looking up the docs and CBE reference for find. They type find in their IDE, they get what they expect. And then also, if you remember from the start of the talk, a lot of this power is from generic programming. So you could be writing some template that doesn't actually have a concrete struct that's passing in there, but there could be some other const expr stuff happening, saying like, oh, if my types are this, or some other metaprogramming decision I've made, then I'm going to create a sequence policy, and in some other condition, I can create a parallel policy. And so that will work in the template, because it's still fine, and just use the metaprogramming to choose what empty struct you pass in. If they had different names, you would have to have if const expr call this name, if const expr call this name, if const expr call this name, and we're back to C land of a log with L and F on the end. Also, with overloads and classes, member functions, and virtual, watch out for hiding, and things can get a little funky. So we have struct B. It has a virtual function foo that takes an int, and then struct D that inherits from B1, and it has a foo that takes a double. So if we construct D, call foo42, show of hands, is it going to be option 1? Or is it going to be option 2? All right, yeah, folks in the room got it, option 2. I think I'm probably leading with these questions when I say watch out. But yes, indeed, option 2 is called because, again, we're going to search up our scopes, looking for names. In D, we found the name foo. There's only one function, foo, job done. Yeah, it's not an exact match, but integers are convertible to doubles, so it will work, and we call option 2. Yes, please. The question about overriding, and I think it might be answered in the next slides, but if it isn't, ask me again. So now here's where it gets a little bit more confusing. In this case, I was not calling foo through a pointer. But imagine I create a D object, lowercase d, then I take the address of that and store it in a pointer of type B1, and then I call foo through that pointer. Is it option 1? See a lot of hands? Yes, it is indeed option 1, because through the pointer to B, we're now calling the virtual interface, and we're getting foo. But if we had an override in our derived class, and we call to that pointer, so in this case, we have 2 overloads in D, one that takes a double, one that takes an int, that's our virtual function. And in this case, if we call on our B pointer foo42, we're not going to actually be doing overload resolution with the double, but we're finding this virtual function name, and there's an override in struct D, and so we call the foo, and we get option 2. And I would suggest this is going to be a lot less confusing to maybe avoid mixing and matching virtual, non-virtual. There's definitely use cases where you don't want to do that. Like maybe you have some convenience overloads and one that's the true customization point, and they're all just calling each other. But keep your whole overload set in the base class. You don't want to be adding more overloads in the derived classes, because you're just going to get into the hiding problem from earlier, and then it gets more confusing because hiding problems happening if you're using, references, and if you're calling through pointers, you're going to get the virtual dispatch, and it gets quite confusing, and you just really don't want to be in a situation where you have to think about this. Now, yes, please. Repeated it, but yeah, the question was about the override keyword being optional, that if that function signature exists as virtual in the base class, it's going to automatically be virtual in the derived class, and the override is just kind of modern syntax for checking that stuff. But the foo double does not participate. It doesn't become virtual just because of the name, as the whole function signature describes it's virtual. Okay, if you're interested in some controversy on the issues with C++ core guidelines, as we're running low on time, if you noticed, all of my examples, pretty much, I was passing by value. You can also overload using L value references and R value references, and functions will be chosen based on the value categories of what's being passed in. This chart mostly makes sense, but also there's some arguments that maybe if things are cheap to move, you also should pass by value. A few of my colleagues started threads on. There's a lot. My colleague of mine, Russell McClellan, started a giant thread about this. Titus Winters did. This is a bit controversial. This is actually one thing I like about Herb's CPP2, is that within and out parameters are named by their purpose. We don't have to worry about all this stuff. But this is kind of showing you this is another way of overloading functions that if I had 2 75-minute talks, I might talk about this, but I'm not, because you should instead go watch Walter Brown's 90-minute talk from the first day of this conference, In Search of the Perfect Return, where he goes into lots of detail about all of this stuff. Yes, please.
He wasn't recording. He doesn't record.
Oh, I forgot he doesn't record. Well, I will go leave a comment on YouTube, and I'll make a chart that explains this, because I was hoping I could direct people to that. And you're right. That's all, I always go to his talks live, so I know he doesn't record. Well, yeah, I'll make a note to when this video comes out. I'll put some references on the video so somebody can find a useful resource on this. But again, that's a talk for another day. And as I said, as we were discussing earlier, one last thing to think about. Function templates, really what they are is a recipe for creating overload sets. And they're much easier to use if you use concepts. I talk about this a lot in my talk from C++ on C last year, how and when to write a C++ template. Thank you very much.